Welcome back to geometry. We are going to continue looking at section 25, transformational geometry, and we're almost done. We have this video and one more. So this video and one more, but we're almost done. Neither of these videos should be terribly long. So let's take a look at symmetry. And we're going to look at two symmetries, regular symmetry like we think of it, but then we're also going to look at some infinite symmetries or symmetries of infinite objects. So the usual ones that we're used to we'll consider first. All right. So usually when we think of symmetry, or I think that we're familiar with this, we're thinking about how can we manipulate a geometric figure and have it end up looking exactly the same as we started. So looking at it from the viewpoint of transformations, what we're looking for is a transformation that preserves the figure. So a symmetry for a figure is a transformation that preserves the figure. So can we do a translation, a rotation, a reflection, or a glide reflection that preserves the figure? And if we can, right, it has some sort of symmetry. So we'll consider the ones that we usually consider first. So rotational symmetry. Can we rotate the geometric figure and end up with the same thing? When we can, the number of times we can rotate it, the number of pieces that we can rotate it in before we get back to what we started with is called the order. Or you can think of it as the number of different rotations that we could do. So let's consider these examples. So if I look at what happens to this point right here, I can rotate this thing about that point. But if I rotate this object around this point, then I could rotate it so that way this point ends up here. Or I could rotate it so that point ends up here. Or I could rotate it so that way it ends up here. Or I could rotate it so that it goes all the way back to here. So that's 1, 2, 3, 4, but I could also do one of two options. I can think of it as rotating it completely around so that way it gets back to where it started, or I can do no rotation and I would end up with the same image. So that gives me 5 different possibilities. No rotation, 1, 2, 3, no rotation is 1, 2, 3, 4, 5 different rotations. So this is order 5. Excellent. So in the same way, for this one, I could rotate about this point, and I could move this point to here or to here, and so on. So this gives me 0 movement, so 1 rotation, 2, 3, 4, 5, 6, 7, 8 different rotations that I could do. So this is of order 8. Now what about the circle? Now in this case, if I consider what happens to this point, I can rotate it a little bit or a little bit more, or I could have rotated it somewhere in between. And in this case, we would actually, I can rotate by any measure that I like. So this is actually of infinite order. All right, so let's consider some objects that aren't just our nice regular polygons or a circle. Here we have what looks kind of like a fan, and I could consider how this point moves. So I could move this point to here, or I could move it to here, or I could move it nowhere at all. So this is of order 3. Now what about this guy, a rectangle? We could rotate that? Yeah, and we can have something that ends up looking the same. So again, look for that center, and I could rotate this point to over here, and then I could rotate it back. So this is of order 2. Excellent. So again, that symmetry, rotational symmetry, and then reflection symmetry are the two that I think that we're familiar with. So a figure has reflectional symmetry if we can reflect the image about a line and we get the same image back. And we can have a lot of lines of symmetry, reflectional symmetry. So I'm going to draw these lines. Let's go with red. Oh, actually, let's go with blue. That'd probably be a good idea. All right, so for a pentagon, right, if I'm looking at a regular polygon, then when I have an odd number of sides, I can consider the line through the middle, through the midpoint of the line segment and the opposite vertex, right? If I reflect it over this, left and right look the same, so when I reflect it, I get the same thing back. But I could do that through any collection of points in opposite sides. So that gives me 5 possibilities for lines of reflection. So there are my 5 lines of reflection. But I could do the same thing where we have an even number of sides. And in that case, if I put a line through 2 vertices, I could end up, right, the image on the left looks the same as the image on the right, so line of reflection. And we could do that for any pair of vertices, of any pair of opposite vertices. But I can do the same thing with the sides as well, right? If I reflect through the midpoint of 2 opposite sides, okay, consider the line passing through the midpoint of 2 opposite sides. Again, image on the left and image on the right look the same, so when I reflect, I end up with the same geometric figure. So I can do that with any pair of opposite sides. So this gives me quite a few, right? That gives me 8 lines of reflectional symmetry. All right, what about a circle? Well, of course, any line that passes through the center of the circle gives us a line of symmetry, okay, a line of reflectional symmetry. For our triangle here, we actually have only 1 line of symmetry. Right? If I were to try and reflect it over this line, I would find that this guy would get mapped to over here, so that doesn't quite line up. So we only have this 1 line of symmetry. And we have 2 lines of symmetry for our rectangle. Split it in half vertically or split it in half horizontally. Excellent. So I think that, again, those are the symmetries that we're familiar with. And what I'd like to do is I'd like to take a look at a couple of examples of these as well. So we're actually going to skip over these 2 symmetries and move on to some examples that look at rotational symmetry and reflectional symmetry. So for these examples, we want to identify, in both of them, we want to identify any reflectional symmetries by giving a line. This is actually a repeat of what we've considered already, so we could quickly give these if we wanted to. Right. Those are our lines of reflectional symmetry, and we already said that it has rotational symmetry of order 5. So I can add that comment as well. Rotational order 5. So here we have a hexagon, and in this case, I could rotate it 6 different angle measures. So I can rotate this for rotational symmetry of order 6, and I can consider the lines of reflection as well. So reflectional symmetry, oops. Reflectional symmetry through the vertices and reflectional symmetry through the midpoints of the sides for 6 lines of reflectional symmetry. For the next image, right, we can't rotate a diamond at all and have it end up the same. So we only have one line of symmetry and no rotational symmetry. All right, for this example, we have no lines of reflectional symmetry. If I were to try and go through this line, of course, that's not going to quite give me what I want. This edge and that edge would line up, but this edge would be going that way. So I don't have any lines of reflectional symmetry. But I do have rotational symmetry. And I can turn it 90 degrees, 180, 270, or 0 degrees. So it's rotational order 4. So we can have a little bit of fun with this and consider some car emblems. And again, look for rotational symmetry, give its order, and reflectional symmetry. So for this example, let's see here. This is kind of like the rectangle, right? And I could rotate it 180 degrees or nothing at all, and I would end up with the same thing. So this has rotational symmetry of order 2. And I also have a couple lines of symmetry, lines of reflectional symmetry, a horizontal line of reflectional symmetry, and a vertical line of reflectional symmetry. All right, any guesses as to the automotive manufacturer here? Do you know? It is Audi or Audi, or however you say that. All right, so next, Dodge. Now this is a little bit interesting. This is, a lot of people associate this actually with the Chrysler emblem. So that's kind of different. You know, if you think about the Dodge emblem, I believe it, actually this may be the Ram. So maybe that was, oh, that looks like an elephant. Okay, no, I don't want an elephant, I want a Ram. Anyway, so we're not concerned about the actual words of the manufacturer, of course. We're just interested in this shape here. And that shape has a rotational symmetry of order 5. Right, because it's just like the pentagon, it just has these pieces pulled out of a solid black pentagon. So what about lines of symmetry? Of course, it has those as well, just like the pentagon did, and it has the same collection of lines of symmetry. Five lines of symmetry. Excellent. So what about the next guy? Rotational, reflectional? Yes. We have reflectional through each one of these points, right? It looks kind of like a triangle. Maybe you have to stretch your brain a little bit to see it that way, but of course it is. So it also has rotational symmetry, much like an equilateral triangle, rotational symmetry of order 3. And what car manufacturer is this? Well, this is Mercedes-Benz. All right, what about Toyota? Well, I can't actually, all right, again, ignoring this part, I can't actually rotate this and end up with the same thing. So no rotational symmetry, but I do have one line of reflection right down the middle here, and only this vertical line of reflection. All right, so what about Hyundai? That is actually how you say that. Watched a video on it because I was really curious. And the manufacturer actually produced the video, so it's not like someone's opinion. It's actually, that's what it is, Hyundai. All right, so for this emblem, right, if I were to draw a vertical line, horizontal line, a little bit off, or maybe this way, no, none of them are lines of reflectional symmetry. The only thing that we can do is rotate it. So rotational symmetry of order, well, all I can do is rotate it 180 degrees to end up with the same thing. So it's a rotational order 2. All right, so that is rotational symmetry and reflectional symmetry. We'll take a look in one more video about translations and glide reflections. Of course, neither one of those two concepts made sense for the examples that we considered so far. So I'll see you guys again shortly, talking about transformational geometry.